Okay, so now we are going to apply these Newton's laws. So what we're going to do is we just take the law that we have just learned, and then we're going to apply it for different cases. So the first case is, let me say you have a mass, and I tell you that this mass is 20 kg, and then I'm telling you that someone is going to apply force that way, and let's say that force that they apply is going to be 80 newtons. And then someone also is going to apply force this way. Let's call it force 2. So this is going to be force 1. And then force 2 is going to be 100 Newton. And then someone also is going to, let's just make it go that way. So someone else is also going to apply a force that way. So there's another force that way. Let's call it force 3. And that force, let me just say that force is going to be equals to 50 Newton. Okay, now the question was going to be find the acceleration. Okay, so the question is find the acceleration of the mass. So we want to know the direction that the mass is going to accelerate in. All right, so how would we go about doing this? All right, so I'm doing something else that I should be doing. Okay, so let me just take it up so that I have everything like that. All right, I just wanted to open some space. All right, now so I've already learned that since I have more than one force, I can find F net, which is the sum of all the forces. So if I sum all these forces, I'll find F net. F net is a vector. All right, and F net is just the sum of all the forces that are acting on the object. All right, these are just the sum. Now this is a vector. So, and then the net force, not just one force, is going to be equal to MA. When you sum all the forces that are acting on the object, that is what is going to be equals to MA. And A is also a vector. Remember, even for you guys that are in high school, if you're watching my videos, when I put this, I'm just telling you that this thing is a vector. All right. And when I don't put this, I'm just saying I'm only considering the size of that thing. All right, so I'll keep reminding you that so that you don't get lost. All right, so I can actually find the sum of all the forces. Okay, now let me see, what forces do I have? I have a force F1, it's a vector. I have a force F2, it's a vector. I have a force F3, it's a vector. And that all of those things, all of these forces combined, they are going to be equal to the mass of the object that I'm looking at minus the acceleration of the object, which the acceleration is the vector. Now you can see, because I'm still saying everything, I'm looking at everything in vector, haven't considered the directions. So I put plus on everything. Now, after this step, I am going to consider the signs. Okay, so this is what I'm going to do. I'm going to take everything that is going this way as positive in the x direction. I'm going to take everything that is in the y direction going up as positive, which means that anything that is going this way is going to be considered negative. Anything that is going down is going to be considered negative. Now again, if you're in metric, don't worry about what I'm doing. This is just to say this is the x, y, z. If you like, if you are still at high school, you can just say this is the x-axis, this is the y-axis. Now, of course, this is going to be the minus y-axis, this is going to be the minus x-axis. It's fine. You can just look at it like this. If you're at varsity, I'm just using this to denote unit vectors. All right. So just be aware of those two. All right. Now again, it would be helpful if you go and watch my videos first. All right. On vectors. Okay. Now let's look at F1. If you look at F1, F1 is facing that way. So which means that F1 is going to be positive. So where I see F1, I'm going to put positive. I'm no longer going to write positive X, Y, I'm no longer going to do that. All right, I will do that when I have the X and the Y. Since everything is on the X-axis, I'm just going to put positive like this. Now, what is that? It's going to be the magnitude. So when I write it like this is the direction is positive. The magnitude or the size of that force, I'm going to call it F1. Now let's look at F2. F2 is facing that way. That's what F2. So it's going to be negative. So I'm going to put negative. The direction is negative. What is the size? The size is the size of F2. Okay. Let's look at F3. F3 is going that way. So it's going to be positive. So therefore, F3 is going to be positive. It is going that way. Now, here's the trick now. I don't know the direction, which direction the acceleration is going to go. I don't know that. Okay. So here I can make an assumption. I can say I will assume that the acceleration will be towards the right. So you're assuming that the acceleration will be going that way. Remember, acceleration is a vector. So you're assuming that the object is going to be accelerating that way. That's what you are saying. You're assuming that acceleration. This is an assumption. You were not told this. You are just tell you to find the direction. They just told you to find the direction of the acceleration. Alternatively, you can just leave it as A, and whatever you find here as an answer is going to be a direction. So you can do two things. Okay. In actual fact, this one is going to be a little bit more easier. So let's just leave this one. I'm not going to assume. So I am just going to say I'm going to leave it as vector A. All right. So I'm just going to leave it as vector A. I'm looking for that vector A. Okay. So when I do that, sometimes it's always good to assume. I'll give you cases whereby I start assuming what's going to happen. All right. So this is going to be vector A. All right. So I'm looking for this vector A. So you can see here what I'm going to do now. What is on the right, I'm going to write it on the left. So I'm going to say MA. So I'm going to show you this step once. Afterwards, whenever you see me swapping things, just know I've done this. All right. So this is what I'm doing. And then my A is going to be equals to F1 minus F2 plus F3 divided by A, divided by M, sorry, not A. And F1 is, we said that F1 is, I don't know why I'm doing this. This is too much. All right, so we said F1 is 80, F2 is 100, F3 is 50. All right, so F1, we said F1 is 80. And then we said F2 is 100. We said F3 is going to be 50. So whenever you see F1, you put 80. Whenever you see F2, you put 100. Whenever you see F3, you put 50. Now the minus signs, they are coming from these ones. The signs are going to come from this step, the step that you did here. All right. And then everything else is going to be divided by 20. Okay. All right. Now, if you look at this, this is going to be the acceleration is going to be equals to, this is going to be minus 20, 50, this is going to be 30 over 20, okay, which is like 3 over 2, this is going to be 1.5 meters per second squared, because acceleration is meters per second squared. All right, now you can see that it is positive. The answer is positive. It came out as positive. So if it comes out as positive, remember you said everything that is positive is going to be going to the x direction, right? Because everything is on the x, the box is not going up or down. The box is just either going to move towards that direction or it's going to move towards that direction, because there's nothing that is pushing it down, there's nothing that is pulling it up. That's how you just know that you are only considering the forces on the x-axis. But I'm going to come to that type of a scenario now, whereby you're going to have two components and then you have to actually look at those two components. All right. So since it is positive, it means that your acceleration, which is a vector, is going to be 1.5 meters per second squared. That is the size. To the right, that is the direction. How do I know that it's to the right? It's because my answer came out as positive. If my answer came out as negative, then it was going to be to the left. All right. So this is one way you can do it. I'll show you the way whereby you are assuming what happens when you assume. Sorry, I did not write right there. All right. So, all right. So that's good. That's fine. Now, let us now look at the case whereby I have the x direction and I have the y direction. All right. So we said to you, according to Newton's law, the sum of all the forces is going to be equal to ma. Now here's the thing. If the force can be in the right direction, you can also have a force that is going up. You can also have a force that is going at an angle theta here. So it depends. You can have forces that are just going in different directions. Maybe this is F2, maybe this is F3. Like you have forces that are just going in different directions. You could have a force that is going down as well. Okay? So you could have this situation here, whereby you have forces that are just going in different directions like this. Now the question is, how are you going to deal with that? Because if you're looking at these forces, you don't know whether your object is going to be going up, or your object is going to accelerate to the right or the left, or your object is going to accelerate down, or your object is going to move at an angle. So meaning that for this case, it's possible that depending on the forces, how big your forces are, it's possible for you to get a case whereby your object is going to move in that direction. So the acceleration is in the x direction if that's the case. Okay. If your object is going to move up, then the acceleration is in the y direction. Okay. And then of course, if your object is moving towards the left, it's still in the x direction. If your object is moving down, it's still in the y direction. But now you can also have a case whereby your object is accelerating this way. So this is acceleration. Now this acceleration, if you look at it, since it is a vector, it is not moving to the right or up, but it is a combination, which means that it has components. So this acceleration has the x component, there's the x component, this is the x component of the acceleration, and this acceleration has the y component, there's the y component of the acceleration. Now, since I don't know what will be the direction of my acceleration, it's always best to break up Newton's 2 into components, right, into x and y. So how you do that? And this is how you can actually solve a lot of problems. So you can say, no, look, the sum of all the forces is going to be equal to ma. I agree. But since I don't know the direction of the forces, it's possible for me to have all my forces on the x and the y. It's also possible for me to have all my forces on the x and y, right? So in that case, it is best that I first sum up all the forces that are going to be in the x direction. So I'm only going to look at the forces that are going to be in the x direction. And those forces will be equal to the mass multiplied by the acceleration in the x direction. And then afterwards, I am going to look at all the forces that are in the y direction. Then those forces are going to be equal to the acceleration mass multiplied by the acceleration in the y direction. So what I'm doing, this is Newton's 2 in vector component form. In vector component form. Okay, and this is a more appropriate way to actually deal with these questions, because it will always allow you to actually find almost any type of a force, right, except circular forces. So if your force is moving linearly, meaning that it's moving in a straight line, you will be able to find the force. Okay, so let's look at an example whereby we can actually use this. I'll start with a simple example. All right, I will start with a simple example. So what I will do is I will have a box. There's my box. It has a mass of 10 kg. Okay, so somewhere on the surface. It is somewhere on the surface. All right. Someone applies a force that is going in that direction. And the force that they're applying, let's call it F1, is 100 Newton. Okay. Let's say that there is going to be a force which is going to be F2. And let's say that force is just going to be 30 Newton. All right. Now let me say somehow something else is also applying a force. So they mean that this box also feels another force. Let's call that force F3 that is going up. And let's just say that force is 80 Newton. All right. Then let's also say that this box also feels another force. And let's say that force is F4. And let's also say the magnitude of that force is going to be 80 Newton. All right. Then I tell you that this box is going to accelerate in this direction. So I am telling you that this box is going to accelerate in that direction, meaning that the total acceleration of this box is going to be in this direction. So the question is, how can I find that acceleration? So they want me to find the acceleration, the magnitude of A. Find A, just the magnitude of A. All right. When I have all of these forces. Now I'm going to do it considering just the component forms. Now when you look at this, so you have to break it down. What are the forces that are acting on the X? The forces that are acting on the X is F1 and F2. Those are the only forces that are acting on the X. What are the forces that are acting on the Y? Well, the forces that are acting on the Y is F3, which is this force. This is the force that is vertical, and then this is F4. That is the force also that is vertical. Okay, so these are the only forces that are acting on the Y. These are the forces that are acting on the X. Now, these forces that are acting on the Y, now, since I am told that this box is going to move in the X direction, it means that these forces are the ones that are going to make sure that this box actually ends up moving in this direction. And that direction is the X direction, which means that the acceleration is going to be in the X direction. Okay, so there is going to be an acceleration in the X direction. Now, since I am only told that this box is going to move in the X direction, then this box is not going to go up and it's not going to go down. So I can say that the acceleration in the Y direction is going to be 0, because this box is not going up and this box is not going down. So that's how I determine that the accelerations are going to be X and Y. Now the total acceleration A will be given by the acceleration in the X direction plus the acceleration in the Y direction. Okay, and if you do it like that, you will actually find that since the acceleration in the Y is 0, so let me take this up a bit so that it doesn't go off your screen. So since the acceleration in the X, it does exist, so I don't know, it's just that I don't know it, but the acceleration in the Y is already 0. So you can see here that the total acceleration of this object is going to be the acceleration due to the acceleration of the X direction. And this is very easy to see because the acceleration is going in the X. So which means that the acceleration AX is going to be the same as A. I am going to do a case whereby this is not going to be true so that you understand the difference between the two. All right. Okay. Now this is what I have and this is fine. This is good. All right. Now since I have this, now let me start doing the calculations. I'm going to sum all the forces in the X direction, and they are going to be equals to MA in the X direction. So what are the forces that are in the X direction? It's F1 and F2. So it is F1 is positive, so I'll put F1 as positive. Then it is F2, but F2 is negative because it's facing that way. I always take X as positive and Y going up as positive all the time. That's what I always do. All right. So according to this conversion reference frame, therefore it means that since F2 is facing on towards the left, the arrow is pointing to the left, I have to take it as negative. Then that is going to be F2. Okay. Now I am told that the object is going to move to the right, and which is positive, so it's just going to be MAX. Now these are vectors, these are vectors. All right. At high school, of course, you don't write these vectors. At university, for instance, in my class, I demand that this is done, right? Because I want students to be aware that they are now talking about a vector and they are now no longer talking about a vector. All right. So if you then do this, you can actually find the magnitude of AX, and the magnitude of AX is going to be equals to F1 minus F2 divided by M. What is F1? F1 is 100 divided by minus 30. So this is going to be minus 30 and then divided by 10. All right, so my acceleration in the x direction is going to be 7 meters per second squared. Now since it's positive, it means that it's going to the right. All right, now which means that my acceleration, my total acceleration A, is going to be equals to AX. Remember we said that the total acceleration is the same as AX, so which means that the magnitude of my total acceleration is going to be 7 meters per second squared, because the other one is 0. Okay, now I'm going to do a case now whereby I am actually going to have something that is not going to move on the right or the left. Okay, and now you'll have to do some assumptions as well. So now it's going to be a little bit complex, and now I'm bringing in some assumptions that you guys have to look at. All right, so let me say, for instance, I have a box, and let's now make it 20 kg. There's my object, 20 kg. There's a force F1 that is applied, and that force is 100 Newton. Then there's another force, but now this force is applied at an angle. Okay, and the angle that this force is applied at, let's make it 30 degrees. Let's call it force F2, and this force F2, let's just make it 120 Newton. Okay, then there's a force this side, let's call it F3, and this force is going to be 30 Newton. All right, and then there's going to be a force that is going down, and let me say the force that is going to be going down, let's call it F. Let's call it, I'll try and make it something, I'll make it accurate. The case that I did before was not very accurate. This one I'm going to make it more accurate. Okay, approximately accurate. Let's call it F4. The force that is going down is going to be equals to let's say 200 Newton, because I don't want to calculate actual factor, can make it easy. I think it's going to be 198, if I'm not mistaken, 196. All right, let's just make it 196. Okay, I'll explain later where am I getting this 196. Some of you may already know because it's towards the end of the year. Some of you may not. Okay, so I'm going to explain how I got this 96 to be the next section that we're going to cover. All right, then let me say that I'm going to have another force that is going to go up, some force, I don't know. So now I have a lot of forces, and let's just say this one is 18 Newton. Okay, now the question is, I want you to find the total acceleration. I want you to find A. Find A. I don't know what I'm doing here. Let's say find A. You want to find the acceleration, the total acceleration A. Now here you are not told whether the box is going to go to the right, it's going to go to the left, it's going to go down, up, or it's going to go towards an angle. So you have to determine that yourself. All right. Now in this case, now it is going to be a little bit complex. So let's do it like this. Let us break down all the forces that are going to be acting towards the x direction. But before I do that, I want us to notice this force F2 here. It is at an angle. And you remember what I said? I said F2, if you look at F2, F2 is at an angle like this. And it is at an angle of 30 degrees. Now you remember when we did vectors, we said you can actually break this into components. You can say this is going to be the x component, which is F2 in the x direction. This is going to be in the y direction, and this is F2, but it's F2 in the y direction. Right? So you can break it down into components, and when you add the two, they are going to give you F2. All right. So which means that now when I'm looking at all the forces, so it means that I'm going to have a force here that is going like that. It's also going to be horizontal, it's F2x. I'm going to have a force that is going up, and this is F2y. So I'm just breaking down this force into components. Now let me draw let me redraw this whole situation with just all the forces that are in the x and all the forces that are in the y. So I have 20 kg. So the question is, what forces are in the x? F1, let's start with F1. F1 is in the x. It's just horizontal. It's pointing that way. So F1 is in the x. Okay, F1. What about F2? Well, F2 is like that. But then I can take the component of F2, which is in the x, and it's going to be this component, which is F2 in the x component, which is this one. This one is going to be the component of F2 that is facing in the x direction. Okay, what other force is in the x direction? There's another force that is in the x direction. It's F3 is in the x direction. Okay, so let's look at the ones that are in the y direction. That's 20 kg. So let's look at the ones that are in the y direction. What do I have in the y direction? Okay, F1 is, I don't have anything that belongs to F1 in the y direction, but I have something that belongs to F2 that is in the y direction, and that is F2y. F2y is in the y direction, it's going up, it's facing up. Again, if you don't understand how I broke this down into components, go and watch my videos on vector. Okay, then I have F5 also, it's going up. F5 is also going up. Then I have F4 going down. Okay, so I have F4 going down. All right, so this is what I have, and now I can actually work through this. Okay, this is what I have, and I will work through this. Okay, now let's see. I am now going to say I will first find the sum of all the forces in the x direction. So I'll sum up all these forces that are in the x, F1, F2x, and then F3. And then those ones are going to be equal to the mass multiplied by the acceleration in the x direction. And this is where the assumption is going to come in. And if true, I will tell you how you are going to say that your assumption was correct or not correct. Okay, I am going to tell you. All right, so let's say I'm going to choose my directions. I'm always going to choose this direction. It's always good to show your examiner what directions did you choose as positive, what direction did you choose as negative. It's always good. Okay, so I'm going to choose this one as positive, this one as negative. All right, so let's see what is going to be the sum of all the forces in the x direction. Well, it's going to be F1. F1 is a vector. It's going to be vector F1 plus the vector F2x. Remember, when they are still vectors, you just write them, all of them as plus F3. So you don't care whether the direction is pointing what direction, you're just writing them. Then this is going to be M-A-X direction. Now this is where now I am going to do the directions. All right, this is where I'm going to do the directions. Now you can make an assumption, or you may not make an assumption. In actual fact, let me drop this assumption. Let's just work it without making the assumption, and then let's just go with it without making the assumption, and then let's see if we're gonna get the direction or not. All right, sometimes you may have to make an assumption. I'll show you cases where you will be forced to come up with an assumption. All right, okay, so this one I think we can do without an assumption. So let's see, F1 is pointing to the right, and the magnitude of F1 is 100. So this is going to be plus F1. Okay, so now I'm dropping the arrows. So F1, I'm going to put the size, the direction is plus, it's positive. Now let's look at F2. F2x is also positive, so I'm going to put a plus. And then I don't know the magnitude of F2x. I don't know how big is F2x. All right, now F3 is negative because it's facing that way. And then it is F3, and then this is going to be equals to the mass multiplied by the acceleration. So I can find the acceleration here. I can already tell that I can actually find it. All right, now I know the magnitude of F1. I don't know the magnitude of F2x. I do know the magnitude of F3, which is 30. So let me go and find out what is going to be the magnitude of F2x and what is going to be the magnitude of F2y. Okay, So if you look at this, they are forming a right angle triangle. And so this is the hypotenuse, this is the opposite, this is the side that is opposite the angle. Okay, so you just draw a straight line, and then whichever side the arrow touches, that side is opposite the angle. Now this side f2x is adjacent, meaning that is just next to the angle. Just all right, so it's adjacent the angle. So if the side you're looking for is adjacent, you're going to use cos. If the side that is opposite, you're going to use sine. So how do I know this? I will say sine of 30 degrees is going to be equals to opposite. What is the opposite side? The opposite side is f2y. What is the hypotenuse? The longest side is f2. Okay, so when I make f2y the subject of the formula, I end up with f2 is sine 30. So that's how I can find f2y. All right, so in the next steps, I'm not going to do this step like this, so I'm just doing this so that you know where I'm getting everything from. All right, so let's do this one. I'm trying to make space. All right, so this one is going to be equals to, so you can see that this one is on the adjacent, so it's going to be the cos of 30 degrees, going to be adjacent, which is this side. Adjacent side is f2x, and then the hypotenuse is going to be f2y. Again, it's going to be f2. Again, we did this when we were doing vectors. I'm just reminding you. So meaning that if I make f2x the subject of the formula, don't cram these things, you must work them out. All right, I'll give you problems now that I've already given you problems in vectors whereby you don't have to cram them. So it would be very beneficial to watch the videos on vectors when you're watching this section. All right, the sound is bad, so I'm going to re-record those videos on vectors, and maybe by the time you're watching these videos, it may be the sound is good, but then it's also possible that if you're watching it just after I've uploaded this, the sound will be bad. So I'm just going to improve on those videos on those ones. All right, so this is going to be f2 cos of 30 degrees at 40 degrees. So this is how I'm going to find the magnitude of f2y. This is how I'm going to find the magnitude of f2x. All right, so what I'm going to do now, I am going to substitute now here. All right, okay, f1 is f1, f2 is going to be, f2x is going to be given by f2 this here, cos of 30 degrees, and then f3 is going to be given by f3. All right, I'm just not putting the values yet, I'm just putting all the signs. This is going to be MA. X is still a vector, so you're looking for a vector here. Now I'm going to substitute. F1 is 100, and then F2, we said that F2 was 120. Let's see if F2 is 120. I think I said it's 120. Yep, F2 is 120 cos of 30 degrees. And then what is F3? F3 I said is 30 Newton. Then what is the mass? The mass is 20 multiplied by this. So which means that my acceleration in the x direction is just going to be, you're going to say it's going to be 100 plus 120 cos of theta 30 minus 30 newtons. You divide everything by 20. I'm doing these steps because some of you, when I skip steps, some students from my experience get confused and they say, I say I'm lost, right? So sometimes I'll try and not skip steps here, but generally I would just skip these steps. I mean, from here I would just go and get the final answer. All right, and you can do that, you're allowed to do that. Okay, then if I put all of this, I don't know what's happening. Okay, if I put all of that, that is going to be equals to f3 is minus 30. I just want to check if f3 is 30. Yeah, f3 is 30, so that is that. So divided by 20, so I get a positive number. I get a positive 8.7 meters per second squared. All right, Some questions would say leave your answer in 2 decimal places or 1 decimal place. Some answers, if the question doesn't say, just leave it in 1 decimal place. All right. Okay. All right. That is what AX is, which means that AX is actually pointing in that direction because it's positive, and the magnitude of AX is going to be 8.7 meters per second squared, and the direction is going to be in the towards the right. That's what this means. Now let's do it now for the Y. So I'm going to say, if I sum up all the forces in the Y, they are going to be equals to MAY. MAY. Okay. Now, what are these forces in the MAY? Okay, I have them here, so I'm lucky. All right. The first one is F2Y. F2Y is pointing up. Then the other one is F4. So remember, I'm writing them as vectors, so I'm putting plus because I'm writing them as vectors. Then the other one is F5, and you are allowed to skip this step and just go to the next step that I'm going to write now. Okay, and then the mass, I don't know. The acceleration is what I'm looking for, so I'll just leave it as a vector. You are allowed to just move from this step and move to the step that I'm going to write now, whereby you are going to say, well, F2 is going to be pointing up, so it's going to be up, F2y. And then F4 is going to be pointing down, so it's going to be minus. The magnitude is going to be whatever F4 is. And then F5 is positive, and then it's going to be F5. Then this is going to be the mass. That. Okay. Now, when you do this, you can substitute now. So F2 is going to be this F2. So remember what F2y was? It was F2 sine of theta. We found that when we were doing those calculations. And then this one F4, I don't know it. It's F4. Oh, I know it. And then this is F5. This is the mass. MAY is a vector. Then you can substitute now. So this is going to be 120 sine of 30 degrees. Then F4 we said is going to be 196. And then F5 we said that is going to be 80 Newton. And then this is going to be 20 AY, like that. All right. And then from this one, which means that AY, I'm just going to calculate everything, the final answer from this equation. So you can manipulate it on your own. Now I'm getting a minus answer. Now I'm going to explain what this minus answer says or means. I'm getting a minus answer. What does this mean now? So now I am going to get the two vectors. So let me just see if everything is fine. F1 was positive and it's 100. Let me go back to my original sketch. Yeah, it was positive and it's 100. This one is also positive and it's angle, then 30 is minus. All right. So this is fine. This is good. Okay. So now what do I have? Now this A1 that is negative, right? Remember Y is either going up or down. So if it's negative, it means that it is going down. So this acceleration is going down. But the magnitude of this acceleration is going to be 2.8 meters per second squared. So I have two types of acceleration now. I have AX, which is going that way, and AX is going to be 8.7 meters per second squared. Then I have AY, which is going down that way, right? And that one is going to be 2.8 meters per second squared. Now, they want me to find the total acceleration, which is A. That's what they are looking for. They are not looking for AX and AY. And I know that if I take the vector A, it's going to be vector AX plus vector AY. All right. So these two, when I add them together as vectors, they are going to give me the total acceleration. So how is that acceleration going to look like? I have the vector AX going that way. So start with the one that in the X direction. This is AX. And then from the head of AX, draw AY. AY is a vector going down. So from that head, I'm going to draw AY. AY is going down. So which means that the vector that I join from the tail of the first vector to the head of the second vector is going to be the total acceleration. So my whatever angle theta that I'm going to calculate, it will be an angle that looks like that. Okay. So if I want the magnitude of A, the magnitude of A would be the square root of ax squared plus ay squared, because these are vectors. Okay. And then this is going to be the square root of 8.7 squared plus, now I know that this is negative, but you don't care about a negative because you're squaring it. So you're just going to put 2.8 squared. And then you'll find that the magnitude of A is going to be the square root of 8.7 squared plus 2.8 squared. All right, which is 9.1. So that's the acceleration. The acceleration is going to be 9.1 meters per second squared. Okay, so that's the magnitude of A. Now, what is the direction of A? To find the direction of A, the acceleration, you will then have to do tan of theta. You will have to say tan of theta, this theta. Now, remember what tan is, right? Tan is opposite over adjacent. What is the opposite side? It's AY. So it's always going to be whatever is on the Y, which is AY, and take it as positive. And then divided by whatever is on the X, and which is AX in this case. All right. So which means that my tan of theta is going to be AY. What is AY? Is 2.8 divided by 8.7. Okay. And then you'll find the answer there. So let me just do it. I'll do it like this here. Now, the next example that I'm going to do, I'm going to skip steps because I have shown you how do you go step by step until you get the answer. So the next ones, I'll just be more focused on the principles and the answers. Okay. So this is going to be 2.8 divided by 8.7, and this is 0.032. All right. Now, which means that this is how this looks. I'm only doing this once. So it means that tan theta is going to be 0.32. That's what tan theta is. So if you want theta, you go to your calculator, you say tan inverse of that, take whatever the number is, 0.32. When you put it in your calculator like this, you are going to get what theta is going to be. Now, then that becomes 10 0.32, and that is 17.7, which is about 18 degrees. Okay, 17.7. So I just rounded off to 18 degrees. Now, where is that 18 degrees? Now, when you write this, maybe your question is saying find acceleration. But your final answer, you must write your final answer, and they are going to mark your final answer. So you're going to lose marks if you leave it like this. So you must put a final answer. All right. So if you want to put a final answer on this one, so what is going to happen is, let me bring it back. All right. So when you write it, you are going to say A is 9.1 meters per second squared. 18 degrees. Now, what is the direction? Remember, your A looks like this. This is how your A looks like. And then we said theta is going to be here, which means that this is 18 here. Now, if you were to draw a Cartesian plane, I'm going to draw it. If you were to draw a Cartesian plane here, it would look like this. This is going to be X. This is going to be Y. This is going to be minus X. And then this is going to be minus Y. So you can see that this 18 degrees is below the positive X-axis. So you're going to say 18 degrees. So it's going to be 18 degrees below the positive, because this is the positive x-axis. The positive, you can say positive, or you can write it as positive. I'm lazy to write positive x-axis. So this way they can find it. Another way you could say is you went to the east and then you went south. So you can say 18 degrees south of east. You could also say it like that if you want. Okay, so either way they will give you your marks. All right, so this is good. I think we are making good progress so far. All right, now I'm going to talk about weight now. Right, there's a force that I said was 196, and I did not tell you where it's coming from. So I'm just going to say now I'm going to consider that force as weight. All right, now If I consider that force, I'm going to find out what is weight. Okay, so that's what I'm interested in now. I want to find out what is weight. However, in order for us to understand what is weight, we need to first understand something about gravitation. Or it says it's just a gravitational force, because that's where your weight is going to come from. All right, so one of the laws of Newton, it was that one of the laws of Newton was that when you have two masses, let me say I have mass m1 and I have another mass m2. Okay, these two masses are going to attract one another. Okay, they are going to exert forces, and those forces will be attracting one another. Okay, so this is the force that m1, all right, feels due to m2. This is the force that m2 feels due to m1. Now, the magnitude of F1, 2 and F2, 1 are going to be the same, but the directions are going to be different. So this is how we write it. We say that the vector is going to be different. So when you look at it as vectors, the directions are going to be opposite one another. So if this one is pointing to the right, this other one is going to be pointing to the left, right? So this is the vector, then this is the size. So the size is going to be equal, but the vectors, the direction, all right, when you're looking at it as a vector, it's going to have the same magnitude but different direction. That's why there's a minus there. So that's very important for you to actually understand. Now this force here, in actual fact, it comes from a certain law of Newton. But it is a law in itself, but then it is also using a certain principle, which is a law of Newton, and that is known as the Newton third law. So I'm going to write it as Newton 3. Okay, so what does Newton 3? It says that whenever one object exerts a force on another object. Okay, so let's say whenever one object, all right, let's call this object A, exerts a force on another object, the second object is object B. What happens? The second object exerts an equal but opposite force. So it's going to be an equal in magnitude, it's going to be an equal force, but it's going to face in opposite direction. So it's going to exert an equal force, but it's going to be opposite. All right, so we're going to come back to this Newton law of gravitation. Right, let's just explain this Newton's third law and then we'll come back to gravitation after that. All right, so what does this mean? Now let me say, for instance, there is a wall. There's a wall. And then there's you are pushing the wall. So the question is, what is happening here? Okay, so we are going to look at this. What is happening there is that there's the wall, there's your hand. All right, so the wall is feeling a force from your hand in that direction. That's what the wall is feeling. So if I was to draw just the wall would feel a force due to you. Let's call it force 1. Now, whatever force you apply on the wall doesn't like to be disturbed. So what the wall does, it retaliates. Okay, so what it does, it applies another force in that direction, and let's call in your hand. So your hand is going to feel a force in that direction, F2. So if we're to go to draw the force that your hand is feeling, your hand will be feeling a force F2. Now what does Neutron Law 2 say? It says that the magnitude F1 and F2 is going to be the same, but the directions are going to be different, and that is why the vectors are going to be like this. And this is very much similar to what you see there in Newton 3, whereby one object is applying a force and the other one is basically retaliating with the same force, if you think of it like that, or is reacting. So this Newton's third law is also known as the for every action there's a reaction force, or for every action there's a reaction, basically is that type of a law. Okay, so this is Newton's third law. Okay, that's how Newton's third law look like. All right. Okay, now continuing from this, now let's go and apply this gravitational law. Say, so what Newton realized was that if you actually have a planet, because this was done for planets, if I have a planet and the mass of the planet is m1, actually let me make a capital letter M because it's a big object. Then I have another planet, let's say another planet mass m2. The Earth is going to apply a force on mass, let's call it F12, but then mass is going to feel this force and is going to apply an opposite force that is the same size but opposite direction. And then now we come to universal law of gravity. Okay, so from this one we can get the universal law of gravity. All right, and let me bring it here. This is known as the Newton's universal law of gravity. All right, so what does that law say? It says that I can find the force, which is the force, the size of the force. I can find the size of the force between the two objects, and the size of the force between the two objects is given by a constant g. So there's some constant g. I'll tell you now what g is going to be. All right, the mass of one planet multiplied by the mass of the second planet divided by r squared. Now what is this r squared? Now this r squared is the distance from the center. So if I draw from the center to the center and I draw a line, it's supposed to be straight, somehow it's not straight, the distance, and I call that line r. So if I was to draw it, if I have m1, if I have m2, this distance from center to center, and I call it r, that is what r is, the distance between the two objects. It's normally taken from center to center. All right, unless your object is very small, and then you can just take it as a point. But otherwise, if you have very big objects, you have to take it from center to center. All right, then that is going to be the distance between the two objects. All right, now what is this g? This g is called a gravitational constant, and the value of g is constant, so meaning that it doesn't change. It's 6.73 times 10 to the power minus 11. The unit is supposed to be Newton, is g, it's supposed to be Newton, yes, meter squared per kg squared. All right, that is what g is supposed to be. All right, now from this thing here, you can actually find out how much force will the Earth actually exert on an object. All right, so let me say, for instance, there's my planet Earth. There's my planet Earth. My planet Earth is very big. Then there's you. You are standing on the surface of the Earth. So if you take the radius of the Earth from the core, the center of the Earth, to where you are, let's say that is going to be the radius of the Earth, and then we just think of your distance. Your distance from the surface to your center is very small compared to the Earth. So you can actually find that the force between the two of you, if I take the force of the Earth, mass of the Earth is like that, and then I take your mass as m. If I wanted to find the force between the two of you, the force between the two of you would be m, mass of the Earth, divided by approximately, it's just going to be re squared, because the distance that you have is very small. All right. If you don't understand why I'm not considering your distance, fine, don't worry about it. All right. This is what is going to be. All right. Now, but then if you think about this here is a constant. This is constant. This is constant. So I can rearrange this and I say this is equals to me divided by, okay, I put g here, divided by r squared e. Okay. Now this gm, so let me put brackets on it, and then maybe you can actually see it. All right. So I'm just going to put brackets on it. So if I put brackets on this constant here, this constant that says g, mass of the Earth, over the radius r of the Earth, I can actually call it a small letter g. And when you actually put these values, you'll find that g is going to be equals to 9.8 meters per second squared. And this is known as the acceleration due to gravity, which means that I can find the force that you are going to feel due to the attraction of the Earth, and that force is going to be mg. All right. And this g here is called acceleration due to gravity. Now you have already seen this. You remember in the chapter where we were doing free fall, we say that there's a ball, you throw the ball up and the ball comes down and then it hits the floor. And we said that the acceleration that is actually this ball is actually feeling if there's no air friction is g. That's what we're saying. We're saying that the only force that was acting on this object was the force that this object feels due to the Earth attracting it. That is why when you jump up, you come down, because as you are jumping up, the Earth is trying to pull you down. So as anything that has mass, the Earth is pulling it down. As long as it has mass, it's going to feel a force of gravity. Of course, if the mass is very small, then the force of gravity is going to be very small. And if the mass is significant enough, the force of gravity is going to be significant enough. So that is why they say the bigger you are, the harder you fall. All right? Because the bigger you are, the larger your force of gravity is going to be. All right? So this force here, that is going to be equals to mg, is what we call the weight. Okay, so I've introduced two things. I've introduced the acceleration due to gravity. I've also introduced weight. Now, how does this weight work? Well, it means that every object, it doesn't matter. The previous example, sometimes I didn't draw mass, I didn't draw weight, and sometimes I did draw weight. But it means that each and every object, I am not going to use that equation. It's very easy to get examples on that equation. It means that every object that is on the surface of the Earth, even if it's not on the surface of the Earth, as long as it's near the Earth, it is going to feel a force. The Earth is always going to try and pull it towards its center, which is going to always feel a force downwards. And that force will be a force due to gravity. I normally write it like this. This is the force due to gravity. Okay, so this is good. And if you wanted the force, let me say, for instance, the mass of this was 20 kg. So what would be the force of gravity for this mass is going to be mg, which is going to be 20 kg multiplied by 9.8, and then this is going to be 196 Newton. And this is where I got my 196 Newtons there. All right, it was before I could tell you. But then if you look at this example here, let me try and go down. Where's that example? This example here. This example here, I told you guys that my F4 is going to be 196. So that 196 that I got here was actually the force of gravity. It was basically my weight. All right. This 196 here was actually my weight. All right. So this is what I have. That's how I knew that if I have 20 kg, my weight is going to be this. Okay. So that's the concept of the weight. All right. So now let's bring another concept. And the other concept now is going to be called the normal force. So this is going to be weight. And now I am going to introduce a concept where I call it, it's not me who's calling it. It's called the normal force. Okay. Now this is the force that is perpendicular to the surface. That is what a normal force is. It's just the force that is perpendicular to the surface. All right. So since I have a surface, let me say I have a surface, and let me try and draw it as straight as I can. All right, this is as straight as I can. Let me say I have an object, and the object has mass m. Okay. Now I already know that since I have a surface, right, and this object, it means that it's somewhere on Earth, the Earth is going to apply a force of gravity. All right. Now, if this object is not falling down or is not going up and is just touching the surface, whenever this object is touching the surface is always going to apply a force that is going to be perpendicular to the surface. That's why we're saying it's normal. It's a normal force because it is normal to the surface. Anything that is perpendicular to something, we say it's normal to that thing in mathematics. All right. So it is normal to the surface. So there's always going to be a force that is called a normal force, which means that if I have an object and my object has a surface like this, the normal force is going to be in that direction. And the gravity is going to be in that direction. If I have an object and the surface is like that, the normal force is in that direction. It's always perpendicular to the surface. Just throw any force perpendicular to the surface. That is going to be the normal force. If my surface is like that, my normal force is going to be this normal force, which is going to be perpendicular. Now, it is not true. I know you guys from metric, you like to always assume that the normal force is going to be equal to the weight. It is not true. There are cases whereby it will be equal to the weight. There are cases whereby it is not going to be equal to the weight. So let's just do calculations and see when will it be equal to the weight, when will it not be equal to the weight. So let me say, for instance, I have an object of mass 20 kg. Okay, 20 kg. And this object is on the surface. Now I say to you, find me the normal force. Okay, so I want you to find the normal force for this object. All right. So if you have to find the normal force for this object, so there's going to be the force here due to gravity. Then the surface is going to exert a normal force. So how can I find the normal force? Okay, so this object is not going to the right, it's not going to the left. It's not also going up, it's also not going down. What does that mean? It means that AX is 0, AY is also 0. Okay, because it's not moving. All right, if I say this object is not moving. So I don't care about the forces on the X because there's none. I only care about forces in the Y. And that is going to be equal to MAY. What are the forces on the Y? It's Fn, which is going up. And then it's Fg, which is negative. Why? Because I always choose X going that way, positive. So anything pointing up is positive, anything pointing down is negative. This is going to be the mass. Now the acceleration I said is going to be 0 because this thing is not moving up, it's not moving down. So this is going to be 0. Okay. So this is going to be multiplied by 0. All right, it's a 0 vector, but I'm just going to write it as 0. So which means that Fn minus Ft is going to be 0. That's how I can actually find out what's going to be my normal force. Okay, now let's see what's going to be my normal force. So I can say then my normal force is going to be Fg. I'm going to take this, put it this side, it becomes positive. It's going to be Fg, which is going to be mg. Fn is going to be mg. Okay, and then what is that? That is 20 multiplied by 9.8. I've already found it. It's 196 Newton. All right, so this is the magnitude and it's going up. All right, so now what happens if, for instance, I put, there's no need actually. I can write it here. Okay, so the question is, what happens if I actually include two boxes, like stack boxes on top of each other? All right, so what will happen then? All right, so let me try and take this thing up. All right, so if I have two boxes, now let me just put two boxes. One box is going to be 50 kg and another box is going to be 20 kg. All right, now this is a very good example because it's going to actually just include everything. Like we are going to do the weight, we are going to do the normal force, and we are also going to do Newton's laws. Okay, so this is what I want you to do. I want you to find out the upward force. What would be the upward force that would be felt by this box here, 20 kg, and what would be the upward force that would be felt by the 50 kg. So in order to get that, you have to break it down. If you look at the 50 kg box, it is going to feel this force. It's going to feel there's a box on top of it. So it's going to feel a force due to that box. Let's call that box F. If I call this M1, I call this M2. All right. So this is going to be the force that 2 exerts on 1. Okay. And then this is going to, because there's weight here, the gravity is always going to work. So this is going to be gravity of 1. Okay. So there's going to be weight due to that box. And now the surface is going to try and balance this box. If it's not moving, it's not going up, it's not going down, it's not going to the right, it's not going to the left. The surface is going to apply a force that is going to go up. That is going to try and balance these forces, and that is going to be the normal force that will be applied on box 1. I'll call it Fn1. So I want you to find that normal force. Now let's look at this box here, the second box, 20 kg. What are the forces that are acting on 20 kg? Okay, the forces that are acting on 20 kg is the earth is going to try and pull 20 kg down. So that is going to be force of gravity on 20 kg on 2. But there's a surface here. You can see there's a surface here of 20 kg. That's why 20 kg is not falling down, which means that it is feeling a force, which is F1 on 2, basically. All right. So it's feeling a force that is applied by this box, but it's being applied upward. All right. And then those are the only two forces that are keeping this box basically from going down. All right. So now if you wanted to find out what is going to be the force on this, what is going to be the force on this, what is going to be a force on this 50 kg? Okay. So you're going to say on M1, so mean that you are just looking for the forces on M1, and then this is m2. On m1, I'm just going to sum all the forces in the y direction. They are going to be equal to 0. Why are they equal to 0? Because ay is 0. Since ay is 0, may is going to be 0. So now I'm going to start skipping steps. So whenever I do this, I expect that you now know that what I'm saying is that the acceleration is actually going to be equal to 0. Okay, now let's look at the forces there. What force do I have? I have the force Fn1. What other force do I have? I have a negative force F21. Whatever force I have another negative force Fg1. And all of those forces are going to be equal to 0. All right, so these are the forces that I have. Okay, now I don't know what is this Fn1, so I don't know it. That's what I'm looking for. The normal force, which is the force that is applied by the surface on the 50 kg. This one, the force that is going to be felt by the 50 kg due to this one, it is the force that is because of the earth. The earth is going to try and pull this 20 kg box, and that force is going to be the mass of the 20 kg multiplied by g, which is the weight of the 20 kg. And then this one is going to be the weight of the 50 kg, which is m1g. It's going to be 0. So you can see here, as some of you may have guessed, that the normal force on the box m1 is going to be m1g plus m2g. If you want, this is become m1 plus m2g. If you want, you can also write it like that. So which means that if I was to sum the two boxes and just multiply them by g, which is the weight of the two boxes, it was going to be the normal force. So which is going to be m1 is going to be 50, this one is going to be 20, which is 70 multiplied by 9.8. And when you do that, you actually find that this is going to be 50, which is going to be 70 multiplied by 9.8, 686. All right, so this is the normal force due to this one. Now, I said here I want you to find the upward force that will be felt by the 20 kg, and the upward force that is felt by the 20 kg is this F1, 2, which is like a normal force on 2. This is the same like what is the normal force on 2, because that is the force due to the surface. Remember, there's a box here, there's a 50 kg box here. That's where the surface is coming from. All right, and that is the one that is actually exerting this force, that is Fn2. So here, so on M2, so I'm looking for forces on M2 now. All right, so what are the forces on M2? There's only two forces that are acting there. It's this one, which is the 1, 2, which I will call it Fn2. So which means that it's just that force Fn2, the normal force on M2, and it's going up, so it's positive. And then the weight on M2, Fg2. All right, that's it. And it's going to be equal to 0. Why? Because this box, whenever something is not going up, when it's not going down or to the right or the left, is 0. Okay. Also, okay, I'll come back on that point. So which means that N2 is going to be equal to Fg2, and Fg2 is M2g, which is going to be equal to 20. Is it 20 or 30? I think I said 20 multiplied by 9.8, which is 196 Newton. So that's the force, that one. Let me see if I said it's 20 or 30. Maybe I just changed. Yeah, I said it's 20, so it's fine. Okay, so that's fine. All right, so I think so far so good. Now I have the gravity, I have the normal force, I know Newton's two now, and now the most important thing that I also want to talk about before I move on to what's friction and tension, and then I close the chapter. I'll do friction, tension, and then I'll do inclined planes, and then that should be it on the chapter. All right, before that, how do you know whether the acceleration is going to be equals to 0 or not. Okay. Now let me give you cases. Let me say I have an object. Okay. And there are forces acting on that direction, F1 and F2. Okay. If F1 and F2 are the only forces acting on this object M, and these forces are not equal, then there is going to be acceleration in the x direction. This box is going to accelerate. If I have the box and it's moving at a constant speed, okay, here there's going to be AX, but this box is not going up and is not going down, which means that there is no Vy, whether it's not going up, it's not going down. So meaning that the acceleration on the y is going to be 0. If V is constant, it is possible to have V constant and even have forces. It doesn't mean just because there are forces that's acceleration. For instance, if F1 and F2 are equal, then this box is going to move at a constant speed. I mean, if F1 and F2 are equal, this box is going to move at a constant speed, but it is still not going up and it is still not going down. So there is going to be AX is going to be 0, AY is going to be 0. So you have to consider that, do I have forces? If you have forces, are the forces in that direction equal or not? If they are not equal, there is going to be acceleration. If they are equal, then there's not going to be acceleration. And sometimes it's complicated because you can have like 3 or 4 or 5, even 10 forces in the same in the x direction. So you don't know. So that is where now the assuming is going to come in. All right. And then another one is when you consider it, if I have an object and this object is moving downwards, right? It's moving downwards, but at a constant velocity, right? So V is constant. Then there is no AX because this object is not going to the left or the right. So this one is 0. And also there's no AY because it is moving at a constant speed. But let me say you have an object that is actually increasing the speed. So meaning that it is increasing, it's moving downwards, but it is increasing. Maybe when it's here, the velocity is 20 meters per second. But then maybe when it's here, the velocity is something like 50 meters per second. Whether it's slowing down or speeding up, then there is acceleration. So you are going to have AY. All right, you just don't know it. But AX is still equals to 0. Okay, so that is very important. And this is true even if something is going up. Let me say something is going up. Let me say something is going up. If something is going up, there's something that is going up. It's going up. All right. Maybe the speed here is 20 meters per second. Then maybe here is slowing down. The speed here, let's call it V1, is now 5 meters per second. So it's slowing down. All right. So there is acceleration. So even though the object is going up like this, the acceleration, of course, in this case is going to be going down. All right. The acceleration is going to be going down, but there is acceleration. But AX is 0 because it's not moving in the X on the Y. All right. It is also possible to have an object and you're applying a force on it and such that it's speeding up. Maybe here it is 20 meters per second. Here V1 is 50 meters per second. It's speeding up. So there is acceleration in the Y direction going up, but there's still no acceleration in the X direction. So whenever something is not moving towards the left or the right, there's no X. If something is not going up or down, there's no Y. So there's only Y. If something is just standing still, there's no X and there's no Y. So if I have an object like this, and then this object is not, the velocity is 0, so it's not moving. So in that case, AX is equals to 0 and AY is equals to 0 meters per second squared. All right. So this is how you can actually determine what is happening, how is it happening. Now, a complex case, of course, is going to be a case whereby you have an object. Let me just say you have an object like in an inclined plane. And this object, I'm telling you, that is accelerating in this direction. Now, if you look at that acceleration is like that. So there's going to be an angle theta here. So in this case, this one is a little bit complex. It is going to be an acceleration in the x. There's going to be an acceleration in the y. So both the accelerations are present if it's moving at an angle. All right. So whenever an object is moving at an angle, both accelerations are present. But you can eliminate this. You will see when we're doing inclined planes, we can actually simplify this equation, because when it's like this, it is making it a bit difficult for us to work with. So I'm going to show you a way we can actually simplify such a problem. All right. But in this case, you do have ax and you do have ay, provided that your Cartesian plane is like this. And this is the big thing, that you have a Cartesian plane. Depending on the direction of the Cartesian plane, then you are going to have a different case. All right, this is more complex to solve with this Cartesian plane, so we may have to be careful in solving this. And this is how you actually determine whether there's acceleration in that, and acceleration in that, or no acceleration in that, or whatever the case may be. Okay, now what I'm going to do is I'm going to do one more case whereby the normal force is not going to be equal to the weight. All right, so think of it like I have a lift, then there's a person on the lift. So there's a surface on the lift. But then I'm telling you that this lift is accelerating upwards. So if this lift is accelerating upwards, right, let's just say it's accelerating at 2 meters per second squared upwards, then it means that this person is also accelerating upwards. So what forces are going to be felt on the person, by the person? If I treat the person as just the mass m, and if I tell you that the mass of the person is 55 kg, so this is a very small person, right? Then I want you to find the normal force. The surface here is going to apply a normal force, but the person has weight. So the person has weight, Fg, but the surface is also going to apply a normal force, Fn. Now in this case, since there's acceleration, what you're going to say, you're going to say the sum of all the forces in the y is going to be equal to ma. Okay, may in this case. So the acceleration is y, right? So this thing is the same as you can say, if you want, you can call it may, you can call it a, it's up to you. All right, this is the forces in the y. All right, now what you then do with this thing is, okay, I have this. So what are the forces? The forces, Fn is going up, Fn is going up, the weight is going down. This is going to be m, but then the acceleration is going up, so it's going to be ay. So everything is positive. This is positive on the right. So Fn, as you can see here, I'm going to show you, it's going to be may plus Fg, like that. Okay, so the normal force here, the normal force is going to be 55 multiplied by a, which is 2, plus 55, because remember this is mg. All right, let me not skip the steps because some of you may be confused. This is going to be may plus mg. All right, this is may plus mg. Some, they will simplify this, they will just take out a and then you're left with ay plus g. If you want, you can call this aya, could say, because it's the only acceleration, plus g. So it's the same thing. If you want, you can do that. Now when you do that, this is 55 and then this is 2 plus 9.8, and when you do that, this is 55 multiplied by 11.8. okay, multiplied by 11.8, which is 649 Newton. Okay, so that's what I have here. Okay, So you can see here that the normal force is not going to be equal to the weight. How do I know that? Let's calculate the weight. The weight for this thing is going to be mg. What is mg? Is going to be 55 multiplied by 9.8. And then you can see from here that if you say 55 multiplied by 9.8, you actually get that the weight is 539 Newton. So there's more weight here than you actually do get with this thing here. Okay. Yeah. All right. Sorry, there's less weight because it's 539. Okay. So the weight is 539, but here the normal force is more. It's 649. So this is a case whereby the normal force is not equal to the weight. Whereas the above one, there was a case whereby the normal force was equal to the weight. So you have to be very careful to make sure that you don't always go around saying the normal force is going to be equal to the weight. All right. So that's very important. That's very important. Okay. All right. So now I can actually move towards something that we call friction. Then after this, I will then do tension, and then after that, I will end the chapter with forces on an inclined plane. That's basically how I'm going to end it. All right. Okay. Now, so far we've just spoken about forces, and we don't know where they are coming from. So what happens in reality is that if I have a surface, the surfaces are not smooth. So if they give you a question, they say on a smooth surface, it means there's no friction. But in reality, when you go to, like, you zoom in on the surface is rough like this. So when you have an object, the object is not moving very smoothly. There's a rough surface. Okay. And even the object itself is not smooth. It is like that. When you're looking at the object itself, it is not smooth. It is like that. And the surface itself is not smooth at the microscopic level. So these things, when they interact with one another, they sort of resist one another. So there's friction. So you must overcome that friction as well. So what happens is that if I have this mass and I apply a force, this is my applied force. So of course there's going to be a force of gravity G, but there's also going to be a normal force here. Now the question is, what is the friction? Okay, so as I'm trying to actually pull this thing towards this direction, there's something that is preventing me from pulling this thing. So which means that the friction force is always acting in opposite direction to where I want to go. But there's two types of friction. There's static friction and there's kinetic friction. So we're going to explain the two. Okay, there's another one. There's other types of friction. You do have like rolling friction, for instance, when you're having things that are rolling. But this is for varsity. The rolling one is for university. We don't do it at high school. And we are not going to cover it in this chapter. That's fine as well. All right. Now, here, what is happening is there's sort of a graph that I can draw for you guys. And then that graph is going to show you how actually everything is going to work in that graph. Okay. So what happens is you apply a force. So there's going to be a frictional force here. There's going to be friction. So I'll call it FF. Then there's going to be applied force here. So you are increasing the applied force. What happens as you increase the applied force? Now, as you increase the applied force, all right, so your friction increases. There's a certain point that you reach, and that point is called the maximum point. So as you're applying a force, the particular force that you're going to apply, that is actually going to break. So as you are busy applying the force, the object is not moving. And you are busy pulling, the object is not moving. But there's a point whereby the object is going to start moving. And at that point, we say that you have actually reached the maximum value of the static friction. So you must first overcome the static friction. So when it was not moving, the frictional force that is at play is the static friction. So I'll call it Fs. Once you overcome this point, immediately after that point, the object is going to move, it's going to slide. Okay? And it is going to have a frictional force that is constant, and that frictional force, after overcoming the static friction, the frictional force that is going to be under afterwards, once it starts sliding, is going to be called the kinetic friction. All right, so you can find the maximum value of the static friction. It is going to be equal to the coefficient of static friction. It's different for each and every material or every surface, multiplied by the normal force. So this static friction is dependent on the normal force. And the kinetic friction is also going to be given by the static coefficient of kinetic friction multiplied by the normal force. Now, in reality, this static friction is actually less than or equals to this value here. So at some point, it's going to be equal to this value. Afterwards, and then before that, it's going to be less than that value. So that's how this equation is going to be written. Okay? So which means that you need to know what is going to be normal force in order for you to calculate the coefficient of the friction, whatever friction is. Now we can do an example on this one, just a simple one. Then after this, you'll get more examples of this when we are doing other sections. So I'll just start off with a simpler example, and then after that simple example, then we're just gonna try and actually complicate it a little bit, and then that should be okay for us. All right. Now, okay, so let's just have a case whereby I have a surface. I have a mass. My mass is 10 kg. I apply a force of I apply a force of 150 Newton. Okay, so what is going to happen here? So when I draw it, there's going to be weight Fg. Because there's a surface, there's going to be Fn. And I'm telling you that the coefficient of kinetic friction is going to be 0.2, for instance. If I tell you that is the case, it's going to be 0.2. Or let's just say it's going to be 0.1. There's going to be kinetic friction. My object, I'm assuming, let's make it 200 Newton to be safe. My object, the applied force is going to be to the right. Now the kinetic friction is going to be to the left. So I'm assuming that this object will be sliding. So once it's sliding, there's going to be kinetic friction. There are cases whereby you have an object that is not moving. It's because you haven't overcome the static friction. Okay? So, but then the approach is similar. All right? So in this one, if you say the sum of all the forces in the y, this is going to be 0. Why is it going to be 0? Because this object is not going up, it's not going down, so it's going to be 0. That's why I started telling you how do you decide. So with this one, the normal force minus Fg is going to be 0, which means that the normal force is going to be Fg, which is going to be mg, which is going to be 9, which is going to be 10 multiplied by 9.8, which is going to be 98 Newton. All right, that's how you are going to get the weight, and which is going to be the normal force. Now, what about the forces on the x-axis? All right, now the forces on the x-axis, they look like this. It's the applied force, which is this force, and then it is the frictional force, which is that force. Okay, so on the x-axis, and there's going to be acceleration because this object is going to move. All right, so there's going to be an acceleration, and then maybe they say you must find that acceleration. Let's just say maybe they say you must find that acceleration. So how are you going to do that? Okay, so there is a frictional force. All right, the frictional force is negative. You say the sum of all the forces in the x are going to be acceleration in the x direction. What are those forces? It's Fk, which is negative because it's negative. And then you have Fa, which is positive. It's going to be equal to max. So there's going to be acceleration. Now, what is going to be the frictional force? If you wanted to calculate just the frictional force alone, the kinetic friction alone, what you are going to do is you are going to say it's going to be mu Fk Fn, and that was going to be 0,1 because I said this is going to be 0,1. Fn, you've already found it is 98. That's how you would find Fk. All right, so here Fk is going to be equals to, if you divide that, that's going to be 9.8 Newton. All right, so this is going to be minus 9.8 plus 200, and then m is 10. Then you can actually find the acceleration as a vector, and then there's acceleration as a vector, and this is going to be equals to something, and this is going to be equals to that minus 9.8. It's almost like 290. Okay, so let's just do it. So it's just 200 minus 9.8. All right, and then you just going to divide it by 10. I'll just do it once, so rather than trying and adding everything there. It's 200 minus 9.8 divided by 10. This is going to be 19.02, so 0 meters per second squared. So that's my acceleration, right? My acceleration is going to be that much. It makes sense because my friction is not very big and my applied force is a lot. All right, so this is how you can actually use the kinetic friction. This is how you can calculate it. This is how you can use it in a problem like this. All right, that is how you do kinetic friction, and now or friction in general. And now I'm going to introduce you to tension forces. So now let us do tension forces, and let's find out how we can actually work with tension forces. Okay, now what are tension forces? Now tension forces are forces that you experience, for instance, on something like a rope. Okay, so if I have a mass, for instance, I have a mass, then I have a force, and then I have a rope, so I'm pulling this rope in that direction. Okay, so this rope is going to feel a tension force. Now this tension force is felt throughout, right? So here I will feel some force due to that mass, but this mass also will feel some force due to my force. I'm pulling it there, I'm pulling it here with force F. All right, I'm pulling the rope with force F. So what is happening is that this force is going to be translated, so there's be a tension force that is felt due to my pull here, and so I'm going to feel a tension force. So even if I was to come here, there's going to be a force that way, which is a tension force, and then there's going to be a force that way, which means that the rope is going to feel a force in those two directions like that. Okay, all right, now that is what I call the tension force, and this is the force that is being translated throughout the rope. Okay, and this is very useful because a lot of systems, for instance, in a car, a lot of mechanical systems are actually using the concept of tension forces. All right, even the lift itself is using tension force because a lift is like this, and then there's a cable that actually pulls it up and down, and there's tension force on that cable. Okay, so this concept of tension forces is quite useful. All right, it doesn't have to be a rope. Even a wire like a steel, it will have tension force. Right, so basically anything that is some length L is going to actually try and apply a tension force. All right, so if you're applying a force through some length L, and that length L is in contact with what you are pulling or pushing, you are going to have tension forces basically on it. All right, so that's basically how you can actually think of tension forces. Okay, so how do we use it on a problem? Okay, so let's just have a very simple problem, and then we're going to use it on a simple problem. Now remember, this course I'm not focusing too much on the problems. I am focusing on the principles or the concepts themselves. Okay, all right, so let me say I have let me use a simple example. I have a mass of 15. Let me just use 15 for, okay. Then I am applying a tension force. So there's a rope. I am applying a tension force, and the force that I'm applying is going to be equals to 100 Newton. Do I want to apply 100 Newton? 150 is good, I think. 100 should be fine anyway. It's going to overcome friction. It's fine. I'm applying 100 Newton. Okay. So, and then I'm telling you that the surface has a static coefficient of, the coefficient of kinetic friction is going to be 0.25. I'm telling you that this is going to be 0.25. All right. And then you're applying that. And then I want you to find the tension force T. I want you to find the tension force T on this object. Okay. So that's what I want you to find. I want you to find the tension force T that is going to be actually felt by this object here. Okay. So what is going to happen is that this object is going to feel a tension force T here. That is going to be the tension force T that is going to be felt here. And then there's going to be acceleration. And that tension force T here is going to be actually be this 100 Newton. Sorry, you can't find the tension force. You can find the acceleration maybe. And then let's say that tension force is going to be 100 because it's going to be translated, because here I'm going to apply, here on the rope I'm going to apply 100 Newton, which is this tension. Then it's going to react, and that's why I feel a force here, which is T, and that's the T that is going to be translated on the rope. So if I apply 100, and it's just a case like this, and then I'm just going to actually apply that 100 is going to be my tension force. I'm going to do an example whereby the force that I apply is actually not going to be the tension itself. Maybe it would be good if I do an example like that. All right, let's just say you've got to find the acceleration. Let's just find A in this case. All right, let's just find the acceleration. All right, sorry about that. Okay, so for this one, we always start with the forces. You always draw the diagram. This is the mass. There's going to be the weight, Fg. There's going to be the normal force because there's a surface going up. Then there's going to be tension, because here I'm going to feel tension, and that tension is going to be 100 Newton. Right? Whatever the force is, it's going to be a tension. Then I'm going to have kinetic friction that way. Then I will find out what is going to be the acceleration. And then I can assume that the acceleration is going to go that way. But even if you don't assume, you can just find it in this case. All right. So what is going to be the acceleration? Well, the acceleration is going to be, so in that case, the acceleration is just sum of all the forces on the x is going to be equals to ma on the x. What are the forces on the x? Is the tension. Fk is going to be equals to max. I don't know what is this ax. All right. There's nothing I can do here except to say this is going to be mu k Fn. So I need to find what Fn is going to be. And this is going to be max. Anyway, I'm looking for ax, so that's fine, since I'm looking for ax. All right. Okay. And then from here, I don't think I'll be able to do anything. So I'll call it equation 1. Now Martinez equation is going to come in. Then after that, I'm going to say the sum of all the forces in the y are going to be 0, because it's not going up, it's not going down. Which means that Fn is going to be Fg, which is going to be mg. Then this is equation 2. I'm going to take this equation 2 and substitute it on equation 1. So I'm going to take 2 into equation 1. So T is T minus mu K. So where I see Fn, remember I'm saying Fn is going to be mg. So I see Fn, I'm going to put mg. So I'm going to put mg here. And then this is A. This is m, sorry. Ax. Now I can solve for Ax. And then Ax, the vector, is just going to be T minus mu K mg over m. And this is 100 minus 0.25 multiplied by m, which is 15, 9.8. Let me see if it's not doing that even now. Okay, this is 9.8. I divide this by m, which is going to be 15, sorry. And then my acceleration Ax, and my acceleration Ax is going to be A. Why? Because remember, whenever I say A is equal to Ax plus Ay, so since Ay is 0, whatever Ax is going to be A, which means that A is going to be Ax. So if I find Ax, I found A. That's basically what it means. So I don't have to worry too much. So whatever I find as Ax, that is the acceleration. That is the total acceleration A, which is going to be, this is going to give me the magnitude, and then the plus or the minus is going to tell me whether it's going to the positive or negative. All right. So this is going to be 100 minus 0.25 multiplied by 15 multiplied by 9.8 divided by 15. So my acceleration is 4.2 meters per second squared. All right. So this is how you can actually use the tension to actually find out whatever it is. Okay. Now, for instance, I can give you another problem. A common problem, for instance, that you could say, and I think maybe let's discuss it. If I have M1, and maybe I say this M1 is 15 kg, and then there's a rope between M1 and M2, and maybe let's say this one is 10 kg, M2, and then I apply a force here. Okay, I'm applying a force. This is applied force. No, let me not complicate it. I wanted to complicate it, and then I thought, no, let me not complicate it. All right, and then there's an applied force. Let's assume that this force is going to be the tension. Maybe I should apply it. Okay, let me not. All right, let's say this is going to be 100 Newton. All right, and now you could actually simplify this problem. So what is going to happen here is going to be a tension force here in that direction. There's also going to be a tension force here in that direction. Now, since it's in the same rope, the two tension forces are going to be equal. So I'm not going to discuss this problem. I'm just going to set them up for you. All right. So in this case, if you look at M1 and say, what are the forces that are acting on M1? You are going to have the gravity due to M1. You are going to have the normal force on M1. You are going to have the tension on that direction. Then you are going to have friction. Then you are going to have friction in that direction, which is Fk. All right, the friction on 1. If you're looking at M2, what are the forces that are going to be actually experienced on M2? It is going to be Ft on 2, the gravity for mass 2. It is going to be the normal force on 2. Then you are going to have the tension force in that direction. You are going to have the friction in that direction as well. Kinetic friction 2. So I'm going to say 2. Then there's an applied force here. Now I've been showing you how you can actually calculate everything. So from here, you are assuming, now this is where the assumption is coming in, because you don't know whether this thing is going to move or not. So you're assuming if there is going to acceleration, it's going to move in that direction. All right. If your assumption is not correct, your A is going to be negative. If your assumption is correct, your A is going to be positive. If the question, for instance, was saying find the acceleration. Now, what is the problem on an incline? Let me say I have a box and my box is on an incline like this. And this box has mass M. Okay, and then let's just say this M, and then there's theta here. Okay, afterwards I'm going to make it into a problem. I'm going to give it values. Now the question is, how can we solve this problem? All right, so before we know how can we solve this problem, let us try and do something that you shouldn't do and see if we are going to be able to solve it. If you do something that you shouldn't do. In actual fact, I'll do that when you're doing a problem. We're going to try it. When I put the numbers here, we're going to try it the wrong way and see if we can solve it. Then we are going to try the right way and see if we can solve it on the right way. The right way is what I'm going to explain now. Previously, we used to choose our axes like this. We used to say this is X and this is Y. This is fine, but this one complicates your problem because your acceleration vector becomes like this. Okay? And once it becomes like that, your acceleration vector, and then you end up with a situation whereby you cannot actually solve this problem. Okay, so that's the problem that you're going to have here. Okay, you end up with an acceleration vector like that, and that's a very big problem. So in order to eliminate that problem, you choose your Cartesian plane to be like that. So you choose this to be X. So everything that is going down like this is going to be X. Okay, and then everything that is going up is going to be Y. But now, which means that your axis is sitting somewhere here. When your box, for instance, is somewhere down there, right? If you check it, your Y hasn't moved because your Y axis is like that. So it's still sitting on the X. So the X is still 0. The X is 0 here, and the X is 0 here. Sorry, not the X. The X is not 0. The X is something. If you started here to here, you have moved this distance X. But if you look at the Y, you haven't moved on the Y because you are sitting here when you're here. You are sitting here when you're here. You are sitting here. So you're always sitting on the X axis. So you haven't moved. All right. Maybe let me try and explain it again. This is my X axis. And then this is my Y axis. Okay. So when your box is somewhere here, you are sitting here on the X axis. So your X axis, if your X is 0, this is maybe 1, this is 2, this is 3. So when you are here, your X is 2, but what is your Y? You are sitting on your Y is 0. When you are here, your X is 3 because you have moved from 0 to 3 in the X direction. But in the Y direction, you haven't moved because it's in the still sitting on the X axis. You are still sitting on the surface. So as long as you are on the surface, your Y for all of this is equals to 0. And this is why this becomes convenient, because then your acceleration is only in the x-axis. So which means that A is only going to be AX. All right. Now let's look at the forces themselves. All right. Let's look at the forces themselves and how do the forces look like. So now we have explained the reference frame. So let's look at the forces themselves. Okay. And this is true also if you have something like this, and this is theta, then you have a box like that. Then in this case, your Cartesian plane can look like that. You can have it like that. Say it's X, and then it's Y. So here you can see that I can change my Cartesian plane to suit how I want to solve the problem. You're still going to get the same answer. So you see here, the Cartesian plane for this one was the other way around, and here I'm choosing it another way around. I'm choosing X that way. So I'm always choosing whatever direction of the box, I'm always choosing it as positive. So I can choose or I can play around with my Cartesian plane so that it actually allows me to solve these problems a little bit more easy. All right, so let's go back to the top one. We are going to solve this. We are going to look at the forces for this one. Okay, so how do the forces look like if I have theta here? Okay, so how do the forces look like? Okay, so now let me just do this problem. Let me try and show it. So what do I have here? I have a box that looks like this. So remember, my Cartesian plane looks something like this. This is how my Cartesian plane looks like. All right, so I'm going to use the red pen. This is my y, and then this is my x. This is how my Cartesian plane looks like. All right, you can put it in the middle. If you want to track the middle, it's fine. So let me use the red color for forces. So what are the forces? Remember, the weight is always going straight down like this. The weight is always going straight down like that. So this is going to be the weight. The weight is always going straight down like that. Okay, so that's fine. All right. Now the normal force is always perpendicular to the surface. Now the surface is like this. So the normal force is going to be like that. And this is the normal force. All right, it's normal, it's perpendicular. So the normal force is going to be like that. This is going to be normal. Okay, and now when it's like this, so what do I have? I have FG, and then I have Fn. In short fact, this FG, let me move it out from here and write it somewhere here, and there's a reason for doing that. And then there's going to be, this is the surface. This is how the surface looks like, and then this is how it actually looks like. Now this angle here would be whatever the angle theta is. Whatever the angle theta is, you put it here. And then from there, you can see that if I have an angle theta there, it means this FG has two components. I am going to say this is the component here. I will have this component here. Now this is the component that is perpendicular to the surface, so I can call it F perpendicular. I'm doing this, I don't like doing this, but then I'll do it like this because I've seen the students do it like that. Then this one is going to be F parallel. This is the component of the force that is parallel to the surface. It's parallel to the surface. This is going to be F parallel. Okay. Now we know that Fg, for instance, we know that Fg is going to be equals to mg. All right. So if I have a vector like that, and this vector is mg, that's the F, that is Fg. And then I have theta here, and then I have F perpendicular here, and then I have F parallel here, and then this is 90 degrees. So what is my F perpendicular? Okay, if I want F perpendicular, my F perpendicular is going to be given by cos. Actually, let me just do it like that. Okay, let me just say cos of theta divided by Fg, which means that my F perpendicular is going to be Fg cos of theta, which is going to be Fg, mg cos of theta. What about my F parallel? Okay, which is that component here, this F parallel. Well, F parallel divided by Fg is going to be sine of theta. So my F parallel is going to be equals to Fg sine of theta. And this is going to be F parallel is going to be mg sine of theta. Okay, now let's do Newton's 2 on all the problem, and then let's just see how it looks like when we apply Newton's 2. Okay, So let's do Newton's too. So what I'm going to say is I'm going to say what is going to be the sum on the y-axis? And the sum on the y-axis is going to be 0. Why? Because it's always sitting on the surface. Now, since it's always sitting on the surface, it means there's no acceleration on the y. That's another good way to know whether there's going to be acceleration on the y or not. So it's going to be 0. What are the forces in the y? So in the y, I have these forces. If you look at this, remember how my y looks like, right? I have y like that, and I have my x like that now. So anything pointing that way or that way is going to be on the y. And the only thing that is pointing that way is Fn, and the only thing that is pointing down is F perpendicular. So Fn is going to be positive, Fn. F perpendicular is going to be negative, F perpendicular, and this is equals to 0. Which means that my Fn is going to be F perpendicular. Therefore, it means that my F and my normal force is going to be F perpendicular is mg cos of theta. Alright, so I mean, if you have values, you can just substitute. Now, what is going to be my sum of the forces in the x direction? That is going to be the mass multiplied by the acceleration in the x. Why? Because the acceleration is going to be there. The box is going to slide down with an acceleration. So the box will be moving down in that with that acceleration. Okay, so the box will be moving down. All right, so since the box will be moving down, the sum of the forces in the x direction, there's only one force, is F perpendicular. So F parallel, sorry, F parallel is just the only force that is going down. All right, and that one is positive because I have chosen anything that is going down as positive. So this force is going to be positive, and this is going to be m a x. When I substitute this, actually there won't even be a need for me to do an example of this. When I substitute this, this is just going to be mg sine of theta. This is, I'm assuming that is smooth. All right, this is mg sine of theta is going to be equals to m a x. I don't know the direction of that unless I assume that is going down. If I assume that is going down, then I can actually just say it's going to be like that, meaning that I'm saying it's positive if I assume that it's going down. Right, meaning that if I'm assuming that my acceleration is going that way, then I can leave it like that. Right, so this is going to always be your equation 1, and then this one it's going to vary, this one, but for this case it's going to be equation number 2. Okay, now let me show you how you can set it up if you have friction on the surface. All right, what happens if I have friction on the surface? Still the same problem, but the only problem is I have friction on the surface, and sometimes you can even have an applied force, right? So if I have it like this, and this is theta, and I have friction, and I'm telling you that there's going to be friction, so the surface is not going to be smooth. How will my forces look like? Well, my forces will look like this. There's going to be a normal force going up. There's going to be Fg. Remember, this thing is going to look like that. So theta is going to come here, and which means that I'm going to have F perpendicular to the surface, F parallel to the surface. Okay, and then since this thing is going to be going that way, the acceleration, it means that my friction, my coefficient of my kinetic friction is going to be that one, Fk. So how does it look like? The forces on the x is going to be like this. The forces on the x is going to be Fk, and this one, F parallel, this one on the x. The forces on the y, it looks like that. The forces on the y is going to be F perpendicular, and then F normal. So this is the x and this is the, and you can see in both cases it looks like that. Anything going that way is x, anything going that way is y. This is x, this is y. Okay, so when you simplify these equations, if you follow the steps I gave you guys, Fn is always going to be equals to mg cos of theta. Now let's say the sum of the forces in the x. If I say the sum of the forces in the x is going to be equals to ma in the x. Those forces are going to be minus Fk plus F parallel. It's going to be ma. I'm assuming that a is going to be going down that way. All right, you can call it ax, you can call it a. So in the next step, I'm going to call it a, because in this case, remember I said that if ay is 0, ay is equals to 0, and ax is something, therefore the total acceleration is going to be ax. So this is going to be minus Fk plus F dot ma. All right. Now, when you have it like this, you can just substitute and say this is going to be mu k Fn plus this is going to be mg sine of theta. This is ma. All right. And then from here, what you're then going to do is where you see Fn, you're going to put that. Right, where you see that, you're going to put it here. This becomes mu k, whatever mu k they will tell you, or sometimes they'll ask you to calculate the mu k. This is going to be mg cos of theta plus mg sine of theta is equals to ma. Then afterwards, you can just substitute. If they tell you the mass is 5, maybe they tell you the coefficient is whatever, you can substitute it like that. All right. So this is how you can actually find it for this thing. And for this one, if you wanted to simplify it more when there's no friction, okay, so for this one, if you're trying to simplify the one whereby there's no friction, I mean, you can simplify it. The m's are going to cancel, and then you end up with a is going to be equals to g sine of theta. So it doesn't depend on the mass, this one. Okay, this one doesn't depend on the mass. And then let's just go to the one whereby there's friction. Okay, so the one where there's friction, again, the m's are going to cancel one another, and you are just left with minus mu k cos of theta plus g sine of theta is going to be equals to a. All right, now sometimes you do need the mass. For instance, if I put an applied force there, then you're definitely going to, I need to tell you what the mass is going to be, or maybe I'll ask you to calculate the mass, for instance. Right, then maybe I'll tell you what the acceleration is going to be, unless I want to complicate your lives. Now, so it just depends on the level of which I want to test students. But if you are teaching, if you are testing high school students, we don't complicate matters that much. If you're teaching university students, we try and actually challenge them so that, you know, they get the level of a university student. Otherwise, guys, this is it with this chapter. It was a long chapter, but it was a fun chapter to do, and it's a very fundamental chapter to actually understand. If you have any questions, just drop comments, and then I'll reply to your comments, and then I'll have a nice announcement sometime in the near future. All right. Okay. Otherwise, guys, cheers and all the best.